homeworks. 20%. Attendance and 47. But still, A grade I think will be around 85%. So if you don't come to class, but score almost at the top in the rest, you would still be in good position. होमवर्क जो है वो 5-6 होंगे, ऑलमोस्ट 1-2 वीक। बुक जो है इसकी 2 बुक्स हैं, प्रॉपर जो मैंने देखी है वहाँ पे नाम लिखे हैं, इडियट की बुक है और एक जैंगल की है, दोनों PDF फॉर्म में अवेलेबल हैं। तो मैंने इडियट के कुछ चैप्टर्स अपलोड किए हैं, बाकी भी मैं जो है वो कर दूँगा एक दिन। तो मैं बाहर था तो वहाँ स्पीड बहुत कम थी, तो चैप्टर्स अपलोड नहीं थे बाकी, तो मैं एक दिन में बाकी सारे अपलोड कर दूँगा। सो इससे पहले कि हम आज का जो लेक्चर है वो शुरू करें, सो लेट मी begin by introducing you to the course, that what we are going to cover in this course. So this is a new experiment and we will decide in a couple of years if we should continue with this thing or not. So basically we wanted to teach special theory of relativity and improve upon the electrodynamics, because we think one course in electrodynamics is not sufficient. So that's why we have this combination of the two. So in this offering of the course that I am going to do in this semester, what I have planned is this. So we will begin with the special theory of relativity. We will study kinematics and some dynamics as well, especially the transformations according to special theory of relativity, its postulates or background history. We will try to cover all of that. And the end goal of special theory of जो हम इसमें करेंगे वो ये होगा कि how to transform mass, force, charges, currents from one frame of reference to another inertial frame of reference. The second part will be that we will begin with the Coulomb law, essentially, as an experimental law. And then we will use the special theory of relativity to construct. So this is essentially electrostatics. So we will use transformations of special theory and we will construct magnetostatics. So in a conventional electrodynamics course, what you do is you have a certain set of experiments that tell us that how electric charges behave, what is the force between them. So that's electrostatics. And then magnetostatics is given as another independent experimental law, which was actually derived that way, that when Faraday, they were working with electric currents and the interaction of magnetic field with them, they came up with the laws of magnetostatics. But in this course, we will have only one experimental law, that's Coulomb law, and then we will derive this thing using special theory of relativity. So it means if you have special theory and Coulomb law, magnetostatics follow from it. And then we will use another set of Lorentz transformation. So this will essentially be derived by using the Lorentz force law. So we have this Lorentz force QE for electric field, and then for moving observers we will see that this converts into this thing and we will write how to define this new field B, which is in actually another inertial frame. So then using this transformation we will write in the magnetostatics. And then we will use the Lorentz transformation to go from this electrostatic and magnetostatics to fully time-dependent Maxwell equations. So essentially, the purpose of this part is to show another picture of electrodynamics and why it is the way it is, even though it was derived experimentally, because special theory of relativity was already hidden inside this theory before the theory was presented here independently. So once we have done this, so along the way we will solve few problems. But in this part of the course, my emphasis will not be on solving problems as you do in a conventional electrodynamics course. Okay, you are given some charge distribution, some current distribution, and you are asked to find fields that are radiated by those charges and currents. Instead, we will be more concerned with the formalism and abstract presentation of electrodynamics. So once we are done with this part, then we will go to the third part of the course, which is the interaction of fields and charges, both static and in motion. So this will definitely have two parts. The first part will deal that if we have relativistically moving charges, what are the fields that are radiated by them? Okay. For example, when we have a single charge in uniform motion given, it radiates electromagnetic radiations. We will derive those results, and when the charge is accelerated, it also emits radiation which are different. And still, there are other radiations that are radiated by charges that move in a medium with a velocity that is greater than the velocity of light in that medium. For example, in vacuum this can happen, but in say water, the speed of light is c divided by 1.3. So it means the allowed speed is still c, but the speed of light is c by 1/3. If a charged particle is moving with a velocity that is greater than c over 1/3, but still smaller than c, so v is less than c, but greater than c over a factor of that, then these charged particles emit special radiation, Cherenkov radiation. So we will drive the results for those. And then what happens that when charged particle crosses the boundary of a medium, even though their speed is smaller than this one, then again emit radiation. For example, a charged particle goes from, say, water into air or from air to water. These transition radiations we will study. The radiations emitted by particles in cyclotrons and other orbital motions. So this part will deal with this thing. Then the last part would be that what happens to particles in fields. So we have fields. So if in a certain region of space there is some electromagnetic field, and we have some test charge. So what is the action of fields on the charge? What's the effect? What happens to the charge in the presence of time-dynamic field? Like how we can accelerate charges and how we can trap charges in the fields and so on. So this is the scope of what we are going to do in this semester in this course. And I actually have written something even after this, that if we have time we will discuss how to write Hamiltonians and Lagrangian for charged particles in electromagnetic fields. which you might have learned in classical mechanics course as well, I guess, because it's only like we can study it as an example of the classical mechanics part as well. So this is the plan. So hopefully we are going to be able to go through all of it. But I'm not sure what the speed would be, and I hope that we are able to cover these topics by the end of this semester. And along the way, if you have any suggestion that these topics should be included further, we can definitely arrange some more lectures along the way. And we will be going through this course traditionally, 2 lectures per week, and there will be homework that you will be doing. I will be posting solutions right after the date of the homework is due, that you can see. And the problems in the homeworks would roughly be similar to what is going to come in the exam, even though the problem in the exam will definitely be shorter, because in homeworks we can have longer problems, unless I have a midterm which is take home where we might have longer problems. So we'll see about that. We might have one midterm where you can take it outside of class and okay, so any question regarding the plan of the course? So one good thing about the book by Eliot is this, that it has very extensive historical notes before every chapter. I will most likely be not going through many of them, except chapter 1 that I will go through in this week, mostly because I like it. Okay, so it won't be on the exam, you can skip it. And also because it sets the tone that how not only special theory, but also electrodynamics and physics in general was developed over the ages, and how people struggle with different ideas, and these theories and these equations that we just presented all at once, they have been developed over centuries, where people have been going back and forth on different ideas. So this week I will be mostly historical. We will discuss especially the history of science with respect to velocity of light, and also the nature of light, the debates that have been going on, and how the models were discussed and presented and discarded, and what were the objections. And then from next week we will have mostly mathematical parts. But you should go if you like history, which I think most physicists, especially good physicists, they do like history of science. So I hope you will enjoy those parts as well in the book. Zangul's book is very dry. There's very few historical footnotes here and there. Mostly it's very rigorous mathematics. So the combination of two will give you the flavor of both sides of electrodynamics, hopefully. Okay, so if there are no questions, let's begin. And we will begin with the historical debate on the nature of light. And if one says that the science actually started with the debate on light, it won't be wrong. That is perhaps in humans the most important sense, the sense of light. Like of all of the 5 senses that we have, touch, smell, vision, sound. Sound is also perhaps very important, but perhaps the most important is vision. And it's natural that people have been thinking about vision and how do we see for perhaps as long as people started thinking about things, about their environment and about themselves, in addition to, of course, biology of how animals and humans work, because that was practical for people getting sick and they have to be treated. But in terms of science, I think the discussion on the nature of light was perhaps one of the most important topic. So it's not surprising that the debates on the nature of light began since antiquity. But since historical records of endeavors of people only are available since few hundred years before Greeks, so almost all discussion in natural and social sciences, they begin with 500, 600, 700 years before the Christ. Because before that, most of scientific traditions, they were oral, and some of them were written, for example, in Egypt, but those languages have long been discarded because they were pictorial languages where people communicated by drawing pictures. And since these languages where people use alphabets, and they are still existent until now, and they I think started around 3,000 to 4,000 years ago. So that's why even history in religions, it's almost 4,000 years old. For example, a few hundred years ago, Christianity has been claiming that the universe is only 4,000 years old, because they could only go back in history until that time, and that's when the man was created and everything flowed. So in sciences, even in natural sciences, social sciences, that's why the history only usually starts with discussions from about 1000 BC, which is about 3,000 years from now, in the past. So because the discussion that were there, people started writing, and some books were left over, and then people who wrote books later on, they referred to those books. So even though those earlier books are not available, some references to those books are available. So there are some references to people in that time. So in terms of light as well, as perhaps in many other sciences, one of the earliest record of discussion on science is with Empedocles, or Empedocles, the true pronunciation for this. He was around 500 BC. And this is the man who's credited with this view of the composition of everything in the universe, that they are made of 4 elements: fire, water, earth, and what's the third one? Air. Fourth one. This idea was actually very prevalent, and even today, if you go to some so-called hakim in rural areas, they would still talk about people in terms of these things. So these ideas, which now look to us, especially those people who are trained in modern sciences, very absurd. But this has been very, very effective, and a lot of people have adopted this idea and continue to explain everything in terms of these for a very, very long time. So this was the originator of this idea. And he also had a theory about light, that what light is. It was thought of small particles, and that travel from your eye to the thing that you have to see, and then they bounce back or whatever, and then they come back. So that was his idea of light and being. So about light, he believed that it's particles in motion, and Vegan is like this, that light emits these particles, they are scattered by these objects, and then they come back, and then we see objects. So this thing stuck for a long, long time, more than I think 1500 years. This idea about vision and light remained in acceptance in learned people. Even Aristotle, who is perhaps one of the biggest logician of antiquity, who tried to explain logically almost everything in the universe, how societies work, how heavens work, and how different natural phenomena work. He tried to make a theory about this. Even he accepted this idea about light, that it's made of particles and its vision is this, that the particles are emitted from the eye, and when they come back, you see the object. Aristotle was Greek, so he was, I think, around 300 BC. You can see the exact dates in the book, but that's not the point really. This man was Italian, more strictly speaking, a Sicilian. Sicily is an island in Italy, near Africa. So this was Greek, and as you know, there were a lot of Greek philosophers at that time, because there were academies, and there were almost a proper education system where people would go and live with the teacher for a few years and learn something. So Aristotle had the same belief that these are rays emitted by the eye, and we see the things when it comes back. So this actually idea of vision and light was even held by these experimenters like Ptolemy, who was an astronomer, and even this logician Euclid, who developed mathematics. Even they believed in this one, and they were around 600-700 after Christ in Western world. The first rebuttal to this thing came from an Arab, Ibn Hazm. The spelling is right. So actually, in English, it's usually called Al-Hazm. So he actually rebutted this idea, and that, I would say, only happened as a byproduct of something else that he was doing. He was very much interested in human anatomy. That he would cut the bodies and see different organs and parts, that because like most learned people in those times, they were all hakims as well. That they're not only people who speak wisely, but they're also people who treat people if somebody gets sick. So all these things, medicines and science, they were combined into one person in those days. So he was basically, you can say, an anatomist. So what he did, he tried to understand how eye works, and he would dissect the eyes, and he was the first one who tried to understand the vision, that there is this optic nerve that goes into the brain. So he saw there's nothing in the eye that emits something, or that resembles something that emits. He doesn't have any scientific or other reason to say that, okay, it's not coming from eye. He just looked into the eye to see what's the part that's emitting rays and what's the part that's receiving. So he did see that part where the light comes, and then these nerves are attached to this, then goes to brain. So because of looking into the eye and dissecting it very finally, he was able to say that light doesn't originate in the eye. And actually he also did another important rebuttal of another idea. We will discuss it shortly, but this relates to the speed of light. Most people from antiquity down to even Aristotle and Ptolemy and many big names, Descartes, we will discuss him because of great Western philosopher and scientist. They all believe that velocity of light is infinite. And he was the first one who argued logically that it is not infinite, it is finite, it has to be finite. We'll come to that point later. So he actually contributed to light a lot. And not only this, he also anticipated another very important law in optics, which is usually called Fermat's law of least time, that light travels from one point to another point to a path which affords the least time. So if the medium is homogeneous, so it goes in straight line. If there is a factor index variation, it may take a curved path to minimize the time taken from here to there, because then the straight line would require more time. So he actually anticipated that Fermat's law as well. And you might have studied in classical mechanics, or you probably do, that a law similar to this, that the law of least time from one point to another point, is actually what forms the basis of law of least action, which is just generalization of the same concept, which actually gives a very beautiful representation of physics, of mechanics, not only mechanics but other branches of physics as well, that you can all express everything in terms of Lagrangian, so that the action of something is an extremum. So that law was actually anticipated by him. And he also worked on a lot of things, prisms and mirrors in optics. But for us, the important thing is this, that he said that it doesn't originate in the eye. But still, it's made of particles. That belief actually continued for a while. Simply because everybody saw that light travels in straight line. And people knew from experience with sound waves and water waves that waves generally do not go in straight lines. If you have obstacles around, they will go like this. And since you can hear people who are on one side of the wall, so it means the waves bend, but particles go in straight lines, and since everybody knew light goes in straight lines, so this belief that the light consists of particles was held on for a while. Though, what are those particles exactly? That thing kept on changing, as we will see. So here nobody said what those particles are, but they said, okay, there are some kind of particles, so light is made of those particles that travel in straight line. So one modification happened here, that it's not, it doesn't originate in the eye. And another great doctor of that time, Ibn Sina, as we call him, or Avicenna as he's called by the Western world, he of course agreed with his Arab colleague that light doesn't originate in India. Then let's discuss another great philosopher of Western world, René Descartes. We call the one coordinate system as Cartesian coordinate system. Cartesian refers to anything that is originated or that is referred to the idea of Descartes. And Cartesian are those people who adhere to the philosophy and ideas of Descartes. So, Descartes actually tried to develop a completely new philosophy of universe. Before that, Aristotle and other philosophers, they tried to mingle everything, mechanics and metaphysics and the creator of the universe, they were all intermingled. That these, let's say, the heavenly bodies, they all go around Earth, but there is some heavenly force or something which is taking them around this thing, around Earth. Or later, as for example, people try to say that these planets, they move around Sun, but still, who moves them? There is some extraterrestrial force that does that. So he, and everybody would try to explain natural phenomena by trying to explain it coming out from some fundamental entity that we can't explain, that it is coming from God. Even the philosopher's God was usually different than the God that we have in different religions. Anyway, so he tried to say that this universe that it is a mechanical universe. There are mechanical laws, and this is all mechanical motion, and it should all be explained by mechanics. And then there is a spiritual world, you can say a mindful world or something other. And there are these two words are completely separate from each other, unless there is an intervention from God, which may connect the two. To explain miracles, and perhaps these things are wrong. But so he said that these two words are separate, unless there is some intervention from God at some instant of time or space. So essentially what he did, he separated science from philosophy. And for this mechanistic worldview, he said that we will only take those laws that we can easily prove and that can be proved beyond any doubt. And for that he was a believer that there cannot be anything, no action can be at a distance. Every action has to be through a contact. There is something that is contacting this thing, that this is imparting a force or some action on this thing. This thing here, if there is nothing in between, this cannot influence this thing, no matter what. So he was basically the, you can say, believer of action by contact, or no action at a distance, because that to him that it cannot be proved. We can easily prove that if two things are in contact, one exerts force, there would be action on the other. So now to explain that the light that, let's say, comes out of sun, how does it reach Earth? So since if there is nothing from here to here, this sun cannot affect Earth. So there has to be no sun. So he introduced the idea of a medium between these two, plenum or ether. Ether in Greek, by the way, is called blue sky. So when we look up to the sky, we see blue sky. So we just call this hypothetical medium, that he says that there is a medium between sun and earth which permeates all space, that transmits the force or light from sun to this. And now to explain what light is, he hypothesized that this ether and this plenum is actually composed of fine particles. And the source of light, for example, sun or fire or anything, it's made of other types of particles that are in violent motion. These are static. They don't go anywhere. They're just here. They're part of this ether. And a light source has particles that are in motion. So how do we feel light on Earth, or what light is? It says that the particles in sun which are moving, they tend to move the particles of ether. So let's say ether is yellow, this is ether. And its spellings actually have also been changing. Sometimes it's A-E-T-H-E-R, nowadays I think it's only E-T-H-E. So these light source particle, white particle, they exert a pressure on these things. They don't actually move, but they feel the pressure. And that pressure is transmitted, and that pressure is actually light. So still, light is a sort of particles, just like this, but now the conception of these particles is different from those particles. Those are particles that are like going like this. And these are particles that don't go anywhere and don't actually move at all. They only transmit pressure. So that was his conception of it. And that he said, this is what light is. So the pressure is transmitted, and since it's pressure, he postulated that it's transmitted at infinite speed. Since there's no physical thing that is moving, the speed can be infinite. So the light has infinite speed, and since similarly that pressure, when we feel in the eyes, we sense something. So that was his idea of light. And actually, before Descartes was, his time was around 1595 to 1650. Before him, there was another man, Snell, who has experimentally discovered a Snell's law. Simply by measuring the angles of incidence and refraction between two mediums, he discovered a Snell's law, that this is the relation between incidence and refraction. So that was there. So now, from this thing, he tried to explain that law. And he was actually able to drive that. How? He said, okay, let's say this is a medium. This is a denser medium. This is a rarer medium. And let's say these are the particles. And there is a light source here. So it's transmitting a pressure with a certain velocity. Now, this is a contradiction with his idea, but let's suppose for a while that this pressure is transmitted with a certain velocity, let's say Vi, and then the pressure in the denser medium, let's say, is transmitted with some velocity Vr. So he postulated, since the interface is along this direction, there's no interface or there's no obstacle in this direction. So the component of the velocity in this direction must be continuous across the interface. Because there's no interface in this direction. The interface is only in this direction. So if this is an angle theta I, this is an angle theta R, so this component is Vi sine theta I, and that component is VR sine theta R. So this means sine theta I sine theta R is equal to VR over Vi. And since people knew that in denser medium this angle is smaller and this angle is larger, so if this is larger and this is smaller, so this ratio is greater than 1. So it means this ratio has to be greater than 1. So which means that VR should be greater than Vi. So this was the first testable prediction of the particle theory of light. That if you want to test whether light is particle or wave, just check the speed of light in two mediums. I haven't said anything about wave, but let's just say about the particle. If the velocity is greater in denser medium and smaller in rarer medium, the theory kind of is right. And actually you get the same equation whether you think of light propagation as a propagation of pressure in these particles, or just if you imagine light as made of particles. Just these particles which are physically moving. The same argument applies. These particles, they have a velocity Vi and these have velocity Vr. So the component of velocity parallel to the interface must remain the same, and you get the same equation and the same thing. So when you assume particle nature, you get to the same condition. So this was actually a contradiction in his philosophy, that at one hand he's saying that velocity of light is infinite. On the other hand, he's saying the velocity of light is smaller in rarer medium and it's higher in denser medium. But maybe he, I don't know, we might have reconciled by assuming infinity to be not really infinity but extremely large. So anyway, this is a testable prediction of this game. So he introduced ether, we already discussed this. He drives cells now. Okay, so let's now move on to another person, and perhaps the first one to propose that light is not a stream of particles, but it's waves, and that was Robert Hooke. I think he was an Englishman, 1635 to 71. Now, this is the time that people have begun to understand mechanics as well. Galileo was around this time, slightly earlier. He was trying to explain mechanical motion of bodies. Newton was also contemporary of this time. He has developed his Newton's laws. So the understanding of wave phenomena with respect to sound waves and water waves, that has increased a lot. People have begun to understand what sound waves are. And actually, that it's also possible from common experience perhaps as well. That is the motion of the particles of this medium in air or water or anywhere. So it's the motion of the vibratory motion of these particles. So Robert Hooke says that instead of assuming this light to be as if it's a transmission of pressure, these particles actually undergo a vibratory motion. They don't go anywhere, in contrast to that earlier notion of particle motion, but they just vibrate at their position. So this was actually a precursor of wave picture of light. So that was his idea of the nature of light. So it would be interesting how he postulated that, how he came up with this thing. He says that you have a light source, let's say a candle, or anything, a sun, or I don't know what. If this is your ether that has all these particles in it, so if, let's say you have one particle, this is, right now the yellow is the source of light, so let's say. And since this is undergoing a violent motion, as people have begun to appreciate that these flames, since the gases are going on, the source has moving particles. So he says since light goes in every direction similarly, so if there is a particle which is pushing, let's say, this way, and assume there is only one particle, so there is no pressure this way, but light is also going that way. So possibly what is happening that these particles are going like this, and then the ether particle, they're actually undergoing vibratory motion in all directions. So this is your source, which is like going like this. So these particles of ether, they are all undergoing vibratory motion. So essentially he extended this idea. But this was a radically new idea. Because this is a vibratory motion, which is a characteristic of wave phenomena. So essentially he postulated that light is vibratory motion of those particles of ether. And since people knew that for sound to propagate, there has to be something, there has to be some medium. So for light, the medium is ether, which has been postulated by Descartes. So that was his addition to this theory, and he said that it's not a static pressure, and he also explained Snell's law as well with this thing. He explained it differently. He said that so this is some light source. So something these waves. When these waves reach here, so this is wave front gets tilted. So we have a different angle. So he explained refraction using this wave front medium, but he didn't actually made any conclusion about speed of light in these two mediums, if it should be smaller or greater in denser medium. But this was actually a great jump in the understanding of nature of light. And you have to place yourself in 17th century. Nobody has any instruments to see what light is. Nobody even at that moment know if the speed is finite or infinite. There are no clocks. Even Galileo, when he's measuring the motion of bodies, he's sometimes using initially the pulses, the heartbeat, but of course he realizes it's not a regular phenomenon, then he invented that pendulum clock. So the time instruments are also very crude, distance instruments are crude, but people are struggling with this nature of light. So this was actually a very big leap. Newton, who was a contemporary of this time, his lifetime was from 1642 to 1727. Newton was actually, I would say, one of perhaps the finest physicists, because he came up with a very brilliant idea. He said, okay, let's not care if it is particles or waves. It doesn't matter actually. What matters is what laws light forms. And to explain those laws, we can adhere to the a philosophy that tries to explain those laws. And at that time, he said that the particle nature seems to be a bit more closer to explaining the available experimental facts at that time. Not all of them. So what were the things that have to be explained at that time? For example, Newton had discovered those rings. And when light comes like this, and it goes like this, there are colorful rings. These interference rings that we now know because of interference. Nobody was able to explain why do we see colors. Or if there is a soap bubble, like a thin film, why do we see colors on soap bubbles? Newton had a theory about colors because he had discovered that if you pass light from a prism, it disperses into different colors, because these light particles, which were supposed to be of only one type, you can think of that there are several types of particles that composes this white light. So when you have a prism, because different particles have different speeds in these prisms, and everybody believes that the speed in prism is greater than the speed in air because you are assuming them to be particles. So since the particles have different speeds, so they get dispersed. But this theory doesn't explain why do we see interference colors, because nobody is trying to understand the wave theory. The wave theory, on the other hand, can explain these interference colors or these rings, but there are a couple of other things that we cannot explain. For example, Newton has several objections to wave theory. One of the objections was, which was actually very common. If you have a light source here, it illuminates this part, but then there's darkness here. So it was one of the very common objections to the wave theory, that why don't we see light here? If it is wave, we should be able to see light here. And this objection simply was there because people didn't have any idea about the wavelength of light, that how small it is. visible spectrum wavelength of light in less than a micrometer. So there was definitely some diffraction, but it was too small for people to see. So this was an objection, and the wave theory people said, okay, we can't explain it. Then there was another objection to the wave theory from Newton, and that was of polarization. Actually, recently in this time, what has been discovered that light can be polarized. You have a polarizer, you tilt it like this and tilt it like this. The light have two different polarization, and people were not, especially the wave theory people were not able to understand. Because everybody thought of light as wave in terms of sound. That light is this longitudinal vibration of ether particles in ether. So they couldn't explain polarization. So that was, actually polarization couldn't even be explained by particle theory. That's an objection to both theories at that time. And many of the objections were actually answered by Christian Huygens. And he was one of perhaps the biggest supporter of wave theory, even though there was a lot of opposition from the followers of Newton, that particle nature seems more plausible. Even though Newton himself, as I have said, never rigidly adhered to the particle nature. He only had a view that this explains more experimental facts than the wave theory does. That's it. But followers of Newton, they were actually more rigid adherents of the particle theory than Newton himself. But anyway, Huygens, he was the one who discovered polarization. But he admitted that my wave theory can't even explain polarization. But polarization can be discovered by him. He had one of the biggest objections to the particle nature of light. Can you see? Let me explain the phenomenon. Can you see the objection? So we have a beam of light going like this, and a beam of light going like this, and there is absolutely no disturbance of these two beams, even though the two beams cross, right? Can you see what should be the objection on particle theory from this observation? That was known to everyone. Exactly. He says that if this is made of particles, why don't the two beams destroy each other? So that was his one big objection to particle theory of light. That why don't these particles collide and the beams are dispersed in every other direction? So, but he also actually improved upon Robert Hooke's idea, because he generalized from here. If the light source produces an isotropic radiation, that light goes everywhere, and because of this it's vibratory motion, he says that we can actually go further than this and assume that if we have, let's say, a source here, and it emits a spherical, let's say, wavefront like this, each point on this spherical wavefront actually emits spherical wavelets, the waves again. And it is the vector sum of all these vibrations by taking into account the phases that we get the next phase front here and not here. It cancels out inside, and he actually showed this, and it adds up constructively on this side. And he said, why? It again goes to the postulation of ether. So these are all particles. So if he says that if, let's say, this particle vibrated once, it created a wavefront here. So now here are vibrating particles at one instant of time. So why should these vibrating particles only affect the particles on this side and not on this side?
logically these vibrating particles should produce vibrations in all particles around it. So it means this is a source of another spherical wave. And assuming this thing, he laboriously actually proved that this is how the wave can propagate. So this is what we call actually Huygens principle. So, and this way he tried to explain it, this propagation of light. Plus, he also drives Snell's law. He says that you can drive Snell's law by assuming, let's say, light to be a wave, and with different wave numbers in different mediums. So let's say this medium is K1, this medium it is K2. So since the interface is here, the component of wave numbers along this direction must be conserved. Not the velocities, but the wave numbers must be the same here and here, because the interface is along this direction, so only the component along this direction should change, but the component along this direction should remain same. So this way he derives this relation, K1 sine theta I, K2 sine theta R, and sine theta I, sine theta R is K2, K1. Since the wave number is inversely proportional to the speed, so this becomes Vi over V R. So this is a relation that we get from the wave theory, and this is a relation that we got from the particle theory. And there was only one way to settle it decisively, and that was the measurement of speed of light. But in these times, still no reliable measurement of speed of light is available. But anyhow, this was in complete contrast to this. But at least we have now a testable prediction of a theory of insights. So this was his contribution to this debate on the nature of light, that it is composed of waves, and using this idea, he was actually then able to compute the interference and other patterns. If you have a source here and you put a slit here, you can assume that these are all points of sources, and then you can compute the wave in this region. And using this technique, he also demonstrated the interference of light. So actually this experiment was perhaps the one that started converting people from the particle theory to the wave theory. That if you take a sufficiently monochromatic source of light here, let's say a candle or something that has a particular color, you put one slit so that it becomes uniform in phase, and then you have two slits, and essentially you have two sources of light according to his Huygens principle now. So these two can interfere, and just like water waves, they will have constructive and destructive interference, and we will get light and dark band. And in an experiment, he actually showed to people that these light and dark bands prove that this light is composed of waves. But still, people thought of light as a wave, like sound waves, longitudinal vibration in ether. So, because of this theory, he was also actually, because of interference, able to explain these colors of thin films, rings, or everything. So he was able to explain a lot of things, except, of course, this bending and these shadows, simply because the wavelength was very small. And actually, he, I think, was the first one who measured the wavelengths of light. He was not the friend, which friend? Yeah, I think it was friend. So, the next person in this discussion who is now going to tilt the balance even more in wave theory's favor is Fano. He was around 1773. So he actually was a doctor, but he quit medicine to become a physicist. Like many brilliant physicists, he was multi-talented, a linguist, a musician, an archaeologist. He also studied capillary reaction. Why does water rise in capillaries? He worked. Sorry, this is Thomas Young. Sorry, not Fredman, Thomas Young. And he was actually a prodigy at, I think, age 2. That's what he's written in the book. And actually, this double slit experiment is also attributed to Young, not Huygens, sorry. So he was a multi-talented person. He even worked in elasticity. There's a Young's modulus by his name. So he contributed to several branches of science, to water waves as well. He actually first studied water waves and saw why the amplitude of waves rises when the waves go from a wider channel to a narrower channel because of superposition, because there are several wavelets that are making those waves and then they add up constructively over there, so the amplitudes increase. And he uses the same idea to explain interference of light. And then he does this double slit experiment to demonstrate the wave nature of light. And he also explained the interference of light. And he was the first one who actually measured the wavelengths of light using this experiment. And then from this experiment, and also by first measuring the thickness of films, then he was able to measure wavelengths from there and vice versa. That once he knows the wavelength of a particular light, he can measure the thickness of a particular film. And he attributed actually wavelengths to several colors. So the first person who measures the wavelengths of light that we know refer to several lights. For example, red around 600, violet around 400, and the other one in between. And he was also the first one who made a very extraordinary postulate about light, that it is transverse vibrations, not longitudinal vibrations in ether. And I think perhaps he postulated this thing because he worked a lot with water waves before turning to light. And water waves on the surface, they're actually transverse vibrations because the wave goes this way, but the water molecules vibrate up and down. So this thing might have influenced his opinion that he proposed that light is actually transverse vibrations of ether medium and not the longitudinal vibrations. But he does stop there. It was Fresnel who actually proved it. So what Fresnel did, that he took two polarizers which are cross-handed, like one is polarized along one axis, the other is polarized along the other axis, and he saw that both of these beams do not interfere. For example, what you can do is you can take
and put one polarizer here and the other polarizer here. If they are collinear, then you have interference pattern. If they are cross polarized, no interference pattern. And because of these absence of interference when you have two cross polarized light, he confirmed that light is indeed transverse depolarized. And this instantly explained the polarization phenomena itself. Which there was an objection on wave theory and also on particle theory that why how come there is polarization. So because of Young's and Fresnel's work, wave theory actually came on very strong. And Fresnel was also able to observe this bending of light or these diffraction on these short patches by making very close observations. So this biggest objection to wave theory also went on. And we will discuss this very important experiment. Actually, there were two people. What they did, they measured the speed of light in air and water and proved that the speed of light in water is smaller and speed of light in air is larger. That was almost a death knell to the particle theory for a brief period of time. Because this experiment by Physio, this happened around 1850s. And actually this was also the time that Maxwell was working on combining the laws of electricity and magnetism, and by seeing a missing term because of symmetry, the absence of symmetry, he inserted that term and he was able to produce a wave equation for that electromagnetic waves. And he instantly realized, because at almost the same time people have been able to measure the speed of light by doing experiments, and when he plugged in the values of epsilon naught and mu naught in his formula for speed of those newly discovered electromagnetic waves, they were almost the same as those measured values, and he immediately said that this light is actually electromagnetic wave. And since by Thomas, Young and Fresnel it has been shown that it's transverse wave, and his theory was also already showing that electromagnetic waves that are coming out from the theory, they are also transverse vibration of the fields in relation to the direction of propagation. So all these things combine to show that light is indeed wave in nature. And there were people who suddenly was interested in producing those waves in other waves. And there was one person, Hertz, who pioneered the production of electromagnetic waves and light using spark gas. You can begin from simple geometry, like you have two conductors that are very close, and if you produce a spark here, you can get a wide spectrum of electromagnetic waves. But then he made several antennas, and with those antennas he was able to produce the electromagnetic waves and sense, and then suddenly there was Marconi who used those waves to transmit information wirelessly. But in Hertz's experiment, when he was producing electromagnetic wave by sparking, he noticed another thing, that what we now call a photoelectric effect. In his receiving apparatus, sometime, since there was ultraviolet light was also being produced here, that was falling on one of the conductor and ejecting electron. So this unexplained current was explained by another scientist a little bit later, that he wasn't able to see why this is happening. But almost immediately another people, I think J.J. Thomson or some other his colleagues, who discovered that these are actually electrons that are rejected from here because of ultraviolet light that is falling in. So the same experiment that confirmed the existence of electromagnetic wave laid the foundation for its destruction. Because the photoelectric effect, nobody was able to explain why it is so. Because its characteristics that you have to have a frequency of light that is higher than a certain frequency to eject these electrons. This was explained by Einstein by postulating again that light is made of light quanta. But now this conception of particles of light is completely different from these earlier conceptions of particles of light. So roughly we can say that, okay, we went back to the particle theory, but actually it's not. This conception that energy is quantized is totally different from this very mechanical conception, okay, these are balls that are propagating in successive motion. But roughly speaking, it's a similar thing, because now we know that after Einstein there was development of quantum mechanics, that particle and wave picture, they completely merge into each other. You compute probabilities of finding particles and so on and so on. So this is how the wave theory of light developed. Yes?
So even if we assume that light is particle, shouldn't light be traveling at a slower speed in the denser medium?
No.
Because if we assume that light is have some constant force, then in a denser medium it should feel more pressure than rare medium.
No, but you're assuming the light particles to be the conventional massive particles that feel resistance in this denser medium. But here we have no idea what these particles are, and they're definitely not massive. And there's actually another whole discussion that what these particles are. And people said, okay, these are not your regular massive particles, because if they are so, somebody took a diamond, you rub diamond, it shines, it emits light, but it seems like it's neither broken and it can shine as long as it wants, or some bodies that are heated, for example iron, you heat it for a long time, it will keep on radiating, but it's still the same amount of iron. So it means no mass is leaving it. So people thought these are some totally different types of particles, which are not massive. If you go back to this conception, that even here you see in empty topics there is fire, water, earth, and air. So fire or light is different from earth, like massive particles. So here we derived about this relation only to satisfy Snell's law. We don't know what these particles are. Okay. Okay, so what I have presented here is actually only a snapshot of things that I thought are important milestone. The story that is written in chapter 1 is actually much more colorful and I think enjoyable if you read it yourself. And there's actually another very nice book on the theory of on the history of electricity and light by, let's see if it is roughly here. So it's the book by Whittaker, A History of the Theories of Ether and Electricity. So that's also a nice book, that this big book that explains only this part that I have covered in this. So in the next lecture, we will have a historical survey of speed of light, but that's much more, there will be some rigor there as well. We will see how people are able to measure speed of light by looking at stars, and how the speed of light was measured in water and all the way to the brightness and spectrum. So these two lectures, there won't be much on the exams, but it's just a start. Any question, comment? Thank you.